Indoor navigation is a system that interfaces with existing devices such as phones, smart devices, appliances, batteries, and other objects of interest or objects that could be hazardous to emergency personnel, for example, natural gas, fuel tanks, boilers, etc., to reconstruct the area and provide instructions on navigation. This solution has the potential to help users navigate in situations with limited sensory input or external guidance, such as emergency situations, total darkness, aiding those with disabilities, or helping the everyday user just find the keys they lost somewhere in the house. Indoor navigation has a wide range of real-world users that spans from the general public to people with specific sensory needs. We will be focusing primarily on designing for firefighters and first responders that need the navigation of indoors where visibility is difficult, such as smoky environments or in a building that has lost power. Several tasks that indoor navigation can perform are navigating in spaces that can have readily available maps or are at least easy to map. For example, grocery stores, office buildings, doctors' offices, and government buildings. A key functionality being a backtrack feature, where the device will track where somebody has navigated to within a house or building. If the user needs to quickly turn around and leave, the system will guide them in reverse along their exact path. The UI system will integrate with existing devices, particularly phones, utilizing AR technologies that can read the environment for potential or known routes, using either Wi-Fi or Bluetooth depending on the situation and which is readily available. This solution is different from existing Find My Lost Item applications. With a path tracking system, this allows the user to retrace their steps until they get to where they need to be. From retracing one's steps to find a lost set of keys, or to locating a safe path back, or even an alternative route. Our system will utilize a multi-sensory approaches depending on the sensory needs and desires of the user. For example, some users may prefer haptic feedback that communicates similar details. For instance, a long vibration followed by a short one would indicate a left turn, while short followed by long would indicate a right turn. Some users may prefer a detailed voice output that explains which direction to travel. And of course, visual being the use of the actual map on the desired device. Each interview started with our product being described as a device that can map out the interior of a location to help individuals, either those who are visually impaired or in emergency scenarios. Next, we asked questions of the interviewees pertaining to their thoughts on the product, such as what their initial thoughts were on the product, what they might change about the product, or any features that they would like to see in the product. We also asked about any changes or updates they would like to make to the product, such as size and the ability to interface with/access third-party accessories that they already use or might use in the future. We also asked about other products they used, what they specifically liked about those products, and what they didn't. This second line of questioning was used so that we could review those applications to see what the other developers included, which those users seemed to particularly enjoy, with the end goal of implementing some of those features into our own application, as well as understanding the limits that those current products provide and how we could utilize those in our current product. During the interview process itself, it became apparent when talking with the interviewees that in terms of usability and convenience, implementing the application as an Android or iOS app was the best route and for most to use. Additionally, the interviewees also stated that they would prefer having a code system in case of failure to help identify and resolve issues, so that if it were to ever fail during an emergency situation, they would be able to go in, quickly identify what that issue was, and get the product back on track to utilize it and get out of the building, for example, if it were used in an emergency situation.
Hello everyone, and welcome to our presentation for our indoor navigation project. Our group consists of Sean McWillie, Victor Wakelin, Ethan Walker, and Victoria Waugh. Our indoor navigation system is designed to assist firefighters and first responders to navigate an unknown building during low visibility conditions, such as during a fire, when smoke is present, or during a power outage. Some of the features included in our application are a Follow Me feature, which allows the user to track their movements to trace their current location and where they have traveled within a building, a Backtrack feature, which allows users to follow the previous path that they've taken already and find the fastest way out if they need to exit quickly. So this would involve entrance and exit points being pinned on the map and possible routes being derived from either the user's path or an imported map, as you will see later in the storyboards. We also have a hazardous location feature, which allows users to pinpoint anything in the building that could be hazardous, such as a boiler or a furnace or a fuel tank, which, for example, during a fire could pose a serious threat to the firefighters and first responders in the building. The application is designed to be used on a smartphone, so downloadable as a smartphone application, and can also be extended via peripherals. And our input and output modes consist of visual, audio, including spatialized audio, and haptics. And the user will have the choice to choose any of these or any combination of them depending on their needs. So as previously mentioned, our intended user groups are firefighters, EMTs, and other emergency personnel, especially for use in low visibility scenarios where the chances of getting lost or disoriented inside a building are much greater, and which can pose a threat to firefighters, like in a fire scenario. Our application, of course, can be used by anyone, but they are not our primary target. And the focus for our application is on small professional units with specific needs, so that the solution can be made to fit into their operational guidelines and their existing loadout. So the three use cases or scenarios that we'll be presenting essentially correspond to the three different modalities that the user can choose from. So the first scenario is essentially a visual mode where the user has the ability to easily look at the screen to read the information through the application. So this is a case where visual feedback is the primary modality, and audio and feedback can be used as secondary modes. The second scenario is an audio mode where, say, the user wouldn't have the option to look at the screen if they had to be quickly looking at other things like inside a building. So this is a mode where audio feedback would be the primary source of information, and haptic and vision could be used as secondary modes. And the final scenario involves a haptic mode where the user would essentially feel vibrations corresponding to either left or right, or which direction they need to travel and how far they would need to travel. So this is a case where haptic feedback is the primary modality, and audio and vision could be used if the user decides. When the user first launches the application, all three output modes will be enabled, since we don't necessarily know which ones the user does or does not have access to. In this way, the application is designed to mesh well with the choices, abilities, and attention span of each user. The first feedback to the user happens when the application is finished launching. So once the application launches, on the screen the user would see a message that says basically the application is loaded. For the audio mode, there would be like a cheerful success tone or a chime that would indicate that the application is finished loading, or a voice that dictates that the application is ready. And for the haptic mode, there would be 2 short vibrations that would also signify that the application has loaded successfully. After this, the user is then prompted to enter their credentials. In the case of emergency personnel, these credentials would be configured by the emergency unit. If the login is successful, the same success feedback for launching the application would be utilized. If, however, the login is unsuccessful, visually on the display, it would read like invalid credentials, please try again. This would indicate to the user that, say, their password is incorrect or something like that. The audio mode would consist of like a short unsuccessful tone, like a short long tone that would signify that something has gone wrong, or a voice that says to try again. And the haptic feedback is similar to the audio one, except using vibrations where there is one long vibration that would signify that the action the user tried to take was unsuccessful. Once the user has logged into the application, they will arrive at the home screen that will allow them to take their desired next step. To incorporate multimodal feedback, the application will either piggyback off the default settings of the device or the settings that the user had previously chosen. Based on these settings, the default input will be determined by the application to be either touch or voice inputs. The application will also integrate with a voiceover or talkback system on the device itself if it's enabled. The choices on this screen will be to begin navigation, which will essentially start generating the map as the user travels through the building. Load the map, which will allow the user to load a predefined map of the floor plan, which can also consist of the hazardous items within the building. Preferences is the next menu option, and lastly, to be able to exit the application. Starting with the Preferences screen, in the top left will be the back button to return the user to the home screen. And in the middle of the screen will be toggles for the visual overlay, audio feedback mode, and haptic feedback mode. If the device is in audio feedback mode, the application will recite options to the user and then wait for optional voice commands from the user to either disable or enable their chosen modalities. The user can also select which of these enabled modes should be the primary mode of communication. There will also be a low-level configuration mode for customizing and saving workflows so that the entire team can use a standard operating procedure. So when the user wants to begin navigating, they will have the option to load a pre-configured map of the space or begin navigating without a map and drawing their path through the space. Upon either a successful loading of the map or when the application is ready to track the user, there will be multiple indications that the app is ready to use. These will be similar to the methods used to communicate to the user that the app has launched successfully. So for the visual mode, the screen would display either map loaded or navigation ready, depending on which option the user selected. In the audio mode, there would be a chime or a success tone or a voice that would say either map loaded or navigation ready. And in the haptic mode, there would be 2 short vibrations similar to either the application loading successfully or a successful authentication that would signify that the application is ready to navigate. And only the modes that are chosen by the user would be used to signify that the application is ready to use. So any modes that were disabled by the user would not be used here.
In the following slides, we're going to go over the visual, audio, and haptic prototypes, of which we have several variations. The first one is just visual. We created a mock-up of an app, and this is very recognizable from traditional video games. An arrow points you in the direction you're supposed to go, and it's supposed to work in calamitous situations where full vision is not guaranteed, but the user needs to have visual awareness anyways. The idea is that the app works as an indoor map, providing bearing and direction to go into, but is not fully integrated into any other sort of system, so it would just rely on a phone. In this, we have an app. It shows basically a live feed from the camera. So this requires that the phone be pointed out or have a separate camera. It's not something we can rely on existing. So basically, it provides what we could describe as a spool of string that is laid on the floor to help the user go into a place and then navigate back with adjustments based on the safety profile of the environs. And once the user is out and safe, they just close the application, ending the navigation. This framework will carry over into the audio and haptic modes.
In this section, I will be covering the auditory feedback setting, in which I will discuss how users can activate the auditory feedback, the various options available to them, and then provide an example of how this audio feedback would be capable. To start using the application within audio mode, first, the user simply taps the bottom right of the screen to initiate audio feedback, in which case the app will audibly announce the change from visual feedback to auditory feedback. The users can, of course, have the app display multiple forms of feedback through the settings function. The users can then have their device read the various options out loud from the menu of the app to guide through various features available. The application can tell users, either through various tones or through a voice reading of the corresponding action, what the app is currently doing. Upon deciding, the user can then state out loud what they would like the application to do. For example, if a user is controlling the app through the audio functionality and makes the request that the application should close, then the application will either emit a tone that corresponds to shutting down within the settings, or the app will simply use the direct voice functionality to say, application closing. Users will be given the option within the settings to choose if the app responds via direct voice command or through tones. When utilizing the audio feedback mode, there are 4 different options users will have available. The first audio feedback option, known simply as direct audio feedback, is as simplistic as you can get with design. A voice comes through the application to guide the user as they work their way through the environment, using simple commands such as, for example, make a left at the end of the hall, or take the elevator located on your right. This option is for those who simply do not desire the traditional navigational tool, while they themselves cannot directly hold their navigational piece, or, for one reason or another, are unable to use the visual feedback option. The only requirements that are made of the user is that the front-facing camera of the phone is facing the same direction that the user is walking. Otherwise, the application is unable to alarm the user of any obstacles or changes in the path. The next option users can utilize through audio feedback is a directional ping audio loop, in which the user will be given an audible ping sound that will play when the user is moving in the correct direction. If the user encounters something in their path, or diverts off the course provided, the ping will increase in frequency, or play a series of pings in a burst-like pattern. The idea is that the user will have a subtle change in sound to alert them to any immediate variations within their course. But the user will not be required to maintain their full focus on what is in front of them and can still focus on other tasks. This option is designed with the workforce in mind, namely specialized environments in which the user will have to focus on multiple things at once. The third option that users will have is the choice of non-spatialized audio, in which users will hear a baseline sound, such as a hum, a song, or some other audio pattern. The sound will be continuous and will grow louder as the user continues to move in the right direction. Additionally, the user will hear additional audio distortions as they continue to move to indicate if there are obstacles within their path. This option was designed for those who do not desire a traditional mode and find that the pings generated from our secondary audio option do not grab their attention as they would hope. The idea is that, with the user inserting their own self-selected sound, or by using one of the several preloaded sounds available that they prefer, their attention will still be on navigating the environment as well as other tasks they have at hand. The final option is considered to be an experimental setting called echolocation mode, in which the user will hear a sound that will adjust with reverberations as the user moves to indicate obstacles and directions that the user should be aware of. While this function is similar to our non-spatialized audio function, it should be noted that it is still experimental and can utilize vibrations in what is known as the haptic feedback functionality, and is still under experimentation. With all options that are present to the user, it should be noted that the user can use any available audio playback devices, whether they be speakers, headphones, earbuds, or anything else that is considered convenient for the user. In order to hear the directions or updates in path conditions, the haptic mode, while utilizing vibrations to generate instruction, will still be capable of utilizing headphones as well. So, we hope there will be plenty of options for users to choose from. To best demonstrate an example of what audio feedback is capable of doing, let's take a look at the example of SIE, a Spetsnaz medic who has to find a stranded pilot who has been holed up inside an enemy factory behind enemy lines. SIE cannot carry a lot due to the size of his medical kit, and has to reduce his light profile to avoid being spotted. For these reasons, a simple, noise-canceling headset that uses batteries, a radio, and his navigational device is all he needs to make his way to the pilot. The only notable restriction is that, in order to reserve his visual sensory channel to find, treat, and ingress with the pilot, SIE cannot use the visual feedback option to make his way to the pilot. The result is that SIE can use the auditory feedback option to navigate to the pilot, while keeping his other senses, modalities, and utilize COTS headsets provided to him. The only problems that are present within the operation would be the loss of precision due to the lack of hearing, and the possibility of competing with radio transmissions. However, the pros are that SIE can safely and quickly navigate his way to the injured pilot to provide treatment without sacrificing his ability to see around him.
So to re-summarize how the product works, at the top we see instrument 1. Now this, depending on the user's orientation, will rotate or simulate rotation using the panning of the audio, that is, whether it goes to the left or the right or is a mix between the two. This requires tracking the user's position regarding the nearest checkpoint, such as an open door, along the way to their overall goal. So this is different than just open land navigation. It requires point-to-point directions similar to turn-by-turn directions for streets, but adapted specifically towards finding specific egress and entrance points. Now, the middle column, this adds noise or additional information, changing the timbre and the tone of the signal. This is important because in some cases directional audio may not be feasible, but the timbre and tone of the signal changing will indicate proximity or focus, again, depending on the user's orientation in regards to the next egress or entrance point. Now, the third, at the bottom one, is an experimental feature where the reverberation of the signal is changed to indicate something similar to echolocation used by bats. So in this one, the reverberation starts at 0% in audio engineering terms, that's dry. And as the user approaches something, the reverberation will become tighter or have more room added to it. And again, this is experimental, but it's something feasible with commercial off-the-shelf audio technology, and it might be useful in other cases where audio needs to be listened to, but it cannot be paid much attention to. So the dramatic alteration of the signal to make it more spacey and airy or more compressed and intense can help guide people to where they need to go. Now, all of this can be done with commercial off-the-shelf audio technology and uses several patents that I've created on my own that I'm licensing to the University of Maine. Now, these also have runoff in that they can be adapted directly for the haptic mode. So I'm using the example of Schmitty, who is an EMT who has to go into a crowded electronic music festival. And here, audio is not good because it'll be drowned out. Visual is not good because there are people running around everywhere who have nothing to do with this environment or situation. So some sort of haptic feedback or a bass heavy mode is also achievable using commercial off-the-shelf technology. And basically this just emits a low rumble in the direction indicating where to go and how close one is. So our future work is expanding compatibility. Our goal is to drop this technology in on existing technology rather than try to sell people on a brand new device that might not be interoperable. So our design goals are to make this work with Android and iOS platforms, as well as commercial off-the-shelf headsets, especially those by Bose and Peltor, which Peltor does not have much consumer grade stuff, but Bose has lots of things that you can own in your house, but they also make aviation headsets. Peltor is mainly for construction. They have a lot of innovations in noise canceling technology for their headphones, and they are also used by military and EMS. So to expand the functionality, we're looking at basically how do we increase the level of details in indoor maps. These might be different in many ways that compared to street maps because these are proprietary information. A street map is open knowledge, whereas the internals of a building is something proprietary and should be guarded, but also needs to be available in emergency situations. So the privacy and disclosure aspects of this do need to be balanced.
In conclusion, our product is unique from other similar navigation tools like GPS and INS navigation combination, and that it allows business owners and other users to upload layouts of their buildings for constant updates, ensuring that users would always have the most accurate layout of the building available. The accuracy of the system will ensure a user can always rely on their information that they are being given to navigate the environment. Additionally, the wide variety of options for feedback provided to users is far greater than what is seen on other competitors' applications. Our product is capable of not only benefiting first responders and their specialized jobs, as we have covered throughout our presentation, but the app can also be used by an average individual throughout any job or task in an unfamiliar environment. It can aid those who are visually impaired by using our audio feedback functionality. Those who are deaf can use the visual feedback functionality for navigation, and our wide variety of options enable those the freedom to customize their app experiences to best suit them. The application as a whole will enable many people, regardless of background, the ability to navigate new environments quickly and efficiently, which can promote quicker response times for businesses and quality of life for people of all backgrounds. Moving forward, we would like the applications of various users to talk to each other, sending navigational data and discrepancies between users to pinpoint areas of interest, and even show where another user might need assistance, for example, in the event of a downed first responder. However, moving forward, we also want to begin partnering with cell phone manufacturers to ensure compatibility across the wide multitude of devices, and will continue to ensure reliability across the various platforms and operating systems. Additionally, we will continue to improve our already existing modes and the features that each one contains. Thank you for listening to our presentation.
Audio Mode 1. Spatial audio plays in the direction the user needs to go. Audio Mode 2. A discrete pulse plays with increasing intensity and frequency as the user aims the device around the location. Audio Mode 3, audio gains reverberation depending on position and distance. Haptic Mode 1, wearable device, which we are here simulating, increases in intensity and frequency as target direction is faced and approached.